Hexadecimal, or hex, base 16 numbers. People like decimal are base 10 numbers, probably because we have 10 fingers. Computers like binary are base 2 numbers because binary circuits are easier to build. Hex is a bridge between binary and decimal. You can see up here decimal 8 is binary 100 and is hex 8. Binary, bi means 2. Two unique digits, 0 and 1. Decimal, dec means 10. 10 unique digits, 0 through 9. There's also the octal numbering system. Oct means 8. It has 8 unique digits, 0 to 7. When you get past 7, you've got to reuse digits. And today's topic, hexadecimal. Hex means 6. Dec means 10. 6 plus 10 is base 16. Hexadecimal means there are 16 unique digits, 0 through 9, which we all know about, and now A, B, C, D, E, and F. Yes, A, B, C, D, E, and F are numeric digits in the hexadecimal numbering system. You can see decimal 9 is binary 1001. It's also the hex 9. 0 through 9 is the same between decimal and hexadecimal. Blame the 8-bit byte for having to learn hex. 8 bits can be divided into 4-bit parts called nibbles. 1001, 1010, that's 8 total bits, 2 nibbles, 4 bits each. 2 to the 4th equals 16. 4 bits has 16 combinations of ones and zeros. So from 0000 to 1111, there are 16 unique combinations. So hex is a perfect way to display 4 binary bits. Decimal 10 is binary 1010 and is the hex digit A. If we look at an example of a byte of computer memory, a byte is 8 bits. The first 4 bits, 1001, is hexadecimal 9. The second 4 bits, 1010, is hexadecimal A. Therefore, this binary number can be represented by hex 9A. An 8-bit byte can be displayed with exactly 2 hex digits. Viewing memory as binary is terrible. As decimal, it is confusing. Hex is perfect for 8 bits, which equals 2 hex digits. If we didn't have the 8-bit byte, we probably wouldn't be learning hexadecimal. Decimal 11 is binary 1011 and hexadecimal B. The first 10 hex values, 0 to 9, are the same as decimal. But we need 16 unique digits. A represents the digit 10. B represents the digit 11. All the way through F representing the digit 15 in hexadecimal. Yes, absolutely. Hex A is a digit with a decimal value of 10. Yes, absolutely. Hex B is a digit with a decimal value of 11. And of course, E has a decimal value of 14. D has a decimal value of 13. The digits A through F have values in the hexadecimal numbering system. Now, rarely do I request memorization, but I will now. Memorize the 16 hex digits. The 0 through 9 is easy. The A through F you need to concentrate. Look at 1100, known as hex C or decimal 12. Concentrate on A through F. If you know A through F, 0 through 9 is easy. And of course, we will still learn the math for doing hexadecimal conversions. But do absolutely memorize first 16 hex digits, 0 through 9 and A through F. Understand their binary equivalents and know their decimal equivalents. Let's convert hex 5D to decimal. 5D equals 5 times 16 to the first power plus d times 16 to the 0 power. Well, that's just 5 times 16 plus d times 1, which of course d is 13. So we're talking about 5 times 16 plus 13 times 1. If you do the math, that is 80 plus 13. Add those together and you can see hex 5d is decimal 93. What we just did is we converted from a hexadecimal number, 5d, to the decimal number 93. And we did it using powers of 16. Curious. Recall when we converted binary to decimal, we used powers of 2. When we convert hexadecimal to decimal, we use powers of 16 because it is base 16. Let's convert hex 17e to decimal. Rather than write out the full equation, let's just write down the powers of 16. 16 squared, 16 to the first, 16 to the 0 power. That's 256, 16, and 1. As you recall from binary conversion, you can write down the digits underneath the powers. So I'm going to take that 1 and put it under 16 squared. I'm going to take the 7 and put it under 16 to the first. I'm going to take the e and put it under 16 to the 0 power. This is 1 times 256. This is 7 times 16. This is 14, which is the decimal equivalent of e, times 1. Do the math. 256 plus 7 times 16 plus 14 times 1 is 256 plus 112 plus 14. That's 382. Hexadecimal 17e is decimal 382. That's using powers of 16 to convert hex to decimal. Remarkably similar to how we converted binary to decimal. We wrote down the binary number under powers of 2, and we were able to convert binary to decimal. Let's go the opposite direction. Let's convert 63 decimal to hex. Now, to convert from decimal to another base, you divide by the base. This is a base 16 number, so to convert decimal 63, I'm going to divide by base 16. Well, when you divide by base 16, you get a 3 with a remainder of 15, which of course is f in hexadecimal. Here's the math over here. 16 goes into 63 3 times. 16 times 3 is 48, so I subtract out the 48. I get a remainder of 15, which is hexadecimal f. So decimal 63 is hex 3f. Divide by 16, or the base, and read the remainders backwards. Remarkably similar to converting decimal to binary. When you want to convert decimal to binary, you divide by 2 and look at the remainders. When you want to convert base 16, you divide 16 and look at the remainders. Let's do the same thing by writing down our powers of 16. From the previous slide, 16 squared is 256. 16 to the first is 16, and 16 to the 0 is a 1. 63 doesn't fit into 256, so there's nothing under that digit. 16 does fit into 63 3 times. 63 minus 48 is 15, so I'll put a 3 under the 16 and a 15 or an F under the 1. And by subtracting out multiples of 16, I can convert decimal to hex. It's all very straightforward once you understand the pattern. The pattern is divide by the base when you're going from decimal to that base, or multiply by powers of the base when you're going from the base to decimal. Moving on, both binary and hex run out of digits at 16. Look at this line carefully here. At decimal 16, binary adds a new digit. At decimal 16, hexadecimal adds a new digit. Now, why is that? Let's start with decimal addition. We all know how to do this. I have decimal 999, and I want to add a 1 to it. The problem with it is 9 is the last decimal digit. There are no digits past 9. So 9 plus 1 is 0 with a carry of the 1. The 1 plus 9 becomes a 0 with a carry of the 1. The 1 plus 9 is a 0 with another carry of the 1, and since there's nothing here, the 1 just drops down. 999 plus 1 goes from 3 decimal digits to 4 decimal digits, a 1 and 3 zeros. Everybody's done this since the 3rd grade. We all know how to do that. The only difference in binary is this happens much sooner. There is no binary 2. So 1 plus 1 in binary is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And since there's nothing under this 1, it falls down and creates a new binary digit, and it's a 1 and 4 zeros. If you could do this in decimal, you should be able to do this in binary. When you reach all ones, it's time to open a new binary digit. Well, hex is no different. Hex F, which is decimal 15, there is no digit past F in hexadecimal. So when I add a 1 to it, it's the same thing. It's 0, carry the 1. There is no 16 digit. The last digit in hex is F15. So F plus 1 is 0, carry the 1. With nothing underneath it, the 1 falls down. FF plus 1, F plus 1 is 0, carry the 1. 1 plus F is 0, carry the 1. And since there's no hex digit here, the 1 falls down and opens up a new hexadecimal digit. It's simple. In decimal, you run out of digits after 9. In binary, you run out of digits after 1. And in hexadecimal, you run out of digits after F. So F plus 1 is going to be 0, carry the 1. Notice the pattern. When you want to convert base 2, 8, or 16 to decimal, what do? You multiply by powers of the base. So 111 in binary is 1 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0 power. You substitute in the values for the powers of 2, you multiply it and add them, you get a 7. That's how you convert from binary base 2 to decimal. Well, what if you're an octal or base 8? Well, if you're in base 8, this is base 8, 1, 2, 3, you multiply by powers of 8. So this would be 1 times 8 squared plus 2 times 8 to the first plus 3 times 8 to the 0. It's a simple pattern. When going from one base to decimal, you multiply by powers of that base. Here it is again. We have a hexadecimal 4A6. How do I convert hex 4A6 to decimal? Multiply by powers of 16. 4 times 16 squared plus 10, which is equivalent of A, times 16 to the first, plus 6 times 16 to the 0 power. Straight up, consistent pattern. When you want to convert from any base to decimal, you multiply by powers of that base. What if you're going the opposite direction? What if you're going to convert from decimal to base 2, 8, or 16? Well, what's the opposite of multiplication? It's divide. Repeatedly divide by 2 to convert from decimal to binary. Repeatedly divide by 8 to convert from decimal to octal. Repeatedly divide by 16 to convert from decimal to hexadecimal. And read the remainders backwards. That's all you have to remember. That's the only tricky part. It's to read the remainders backwards. The first divide produces the least significant digit of the result. The last divide produces the most significant digit. There you have it. That's converting hexadecimal, base 16 to decimal, and vice versa, decimal back to hexadecimal. 3 number systems that you really want to understand as a computer scientist are binary, decimal, and hexadecimal. And remember, hexadecimal is kind of the in-between. Computers operate in binary. People operate in decimal. Hexadecimal is sort of the compromise between the two, which is understandable by people.